Hello everyone, in this video we're going to do a statics example and we're going to take the good old inclined plane. So here's a 2D representation. We've got a mass, sits on a plane of known, or perhaps it's one of the engineering questions is to find the angle. So let's say this is a right plane and it has some mass. And it's in the field of gravity, downwards. So we're going to draw a free body diagram, and then we're going to apply the equations of equilibrium to relate the important parameters governing this problem. All right, so let's start out the free body diagram. I think in this case it makes sense to take the whole mass. Let's just draw it at this angle for convenience. There's the mass. So it's in contact. This is the boundary. It's in contact with the plane. We're going to represent that distributed contact with a single force called N. It's got some weight. We'll draw through the center of the block. And this block, as you can see, would slide down if it wasn't held in place by gravity. I'm sorry, by friction. So we have a friction force here pointed in this direction. If the block slips, it's going to begin to go down the plane. So the friction force is going to oppose that motion and will be going up parallel to the plane in the upwards direction. Okay, it looks like we've got all the interactions that we think are important. So now we're going to write equations of equilibrium. Okay. So one of the key first steps is to choose a reference frame. We're writing vectors, we're going to take components, we need to do everything relative to a reference frame. So for convenience, let's try this. This is planar, here's the x and y, so z is coming out of the page. If this is a planar problem, then we expect to see three equations of equilibrium. So two related to the force. So the x forces is equal to 0. So the y forces is equal to 0. There are no forces in the z direction. Moments, the only rotation we can possibly have is rotation about axes coming out of the plane. That's in the z direction. So we'll have a moment equation about some point which we have yet to pick or specify in the z direction, which is equal to 0. So three vector equations. We've picked a reference frame, so we expect to have three scalar equations. All right, so based on this x and this y direction, let's resolve these vectors into those components. So for example, this vector here, we're going to write as this one we can write in the y direction as n times the j, and this vector is going to be mg, and this is in some direction that is not actually aligned with I and j, so we'll just give it a different, let's give it E1 as a direction. So we're going to resolve this vector into components that we use here. So we have three vector equations, right? In this case, it goes directly to three scalar equations. So we just group all the terms about I, about j, and in this case about k, and we get scalar equations. So we need to break up this w here. So this is, let's draw this. We'll use some trigonometry. Right. So if this is theta, let's sketch on here. We're going to want to break it up into directions this way and this way. So by some observation in geometry, this is a right triangle. So if this is a right triangle, This must be theta. So we need components in this direction and this direction. So we can take W is equal to sine in the y direction. And it's pointing in the minus direction, so minus j direction. And then, I'm sorry, that's cosine. Cosine in the j direction. And then plus sine in the I direction. So that's the unit vector E, right? And then times the magnitude, mg. All right, so now let's go directly to our scalar equations. If we're going to sum all the components in the x direction, let's sum those. We have one here. It's in the x direction, indicated by unit vector I. It's going in the minus x direction, so we're specifying a right-handed coordinate system. It's plus going this way. It's plus going upwards. So this is in the minus direction. Then we're going to add this W sine theta, so mg sine theta. That's the I term. There's no other terms in this direction, so that's 0. So this was the sum of the x's equal to 0 equation. Sum of the forces in the y direction equation. We have n going in the positive y direction minus mg cosine theta. There's no component of f sub f in the y direction, so this is equal to 0. All right, so let's write the last equation here. Let's choose the center as O, and we'll write moments about that. In that case, we can see that all these vectors do not generate any moments about this. We can look at this and observe that the brick is not rotating. No forces are causing it to rotate. So we're going to get something not too useful when 0 is equal to 0. So in this case now, we have two equations, and we've related the frictional force, mg, the angle, and the normal force. If you use a simple and common model for friction, so let's see, it's static friction at the point of slip, you can actually relate the force of friction times, where this is the static coefficient of friction. And that would be an empirical value that you would get through measurement, perhaps through a table or some reference. Static coefficient friction. Now, using these equations, you could answer some engineering questions that you might have. What angle do I make the incline if I don't want the block to slide down? Or if I have a block of a certain size, what's the minimum size incline so that the block does not slide down?